All right, welcome to this explainer. Today, we're going to take an incredibly cheap piece of hardware and transform it into a high-end engineering tool. If you've ever felt the absolute pain of trying to debug microcontrollers blindly, well, you are definitely in the right place.
Seriously, stop overpaying for dedicated ST-Link debuggers. We're taking a 330 rupee board, specifically the Vicharak Shrike Lite, which is literally about $4, and we're transforming it into a pro tool. We're going to turn this super affordable board into a full ARM CMSIS-DAP hardware debugger, completely capable of real-time variable tracking.
Okay, here's our roadmap for today. Number 1, AI firmware remapping. 2, wiring Shrike to STM32. 3, OpenOCD and GDB setup. 4, slaying the configuration bug. And finally, 5, live debugging victory.
Let's jump right into Section 1. AI firmware remapping. Customizing the debug probe stack. So to make this work, we need to adapt the official Raspberry Pi debug probe software. By utilizing AI pair programming SWD remapping to GPIO 6 and 7 on the RP2040, we guarantee we avoid any hardware flow control conflicts. See, by default, UART hardware flow control uses those exact pins as CTS and RTS. By moving our serial wire clock and data specifically to GPIO 6 and 7, we ensure a totally clean setup on the chip, without crossing any wires with our default UART interface.
The crucial point here is to follow these 4 precise steps to compile the stack so it's tailored exactly for our Shrike Lite. First, clone the official repository. Second, swap out the default board_pico.h file with our new GPI mappings. Third, compile the firmware using CMake. Make sure you use the specific debug_on_pico equals on flag. And finally, just hold the boot cell button on your board, plug it in, and drag that newly minted .uf2 file right onto the drive. Boom, custom firmware flashed.
Moving right along to Section 2, wiring Shrike to STM32, bridging the hardware.
Having the right firmware is really only half the battle, right? Take a look at this physical battlefield. We have the STM32 target board, often called a blue pill, on the left, and our Vicharak Shrike Lite on the right. We are focusing purely on the STM32 programming header pins, specifically DCLK and DIO, and mapping them directly to our newly assigned GPIOs on the Shrike. To make sure communication is flawless, you must precisely wire Shrike GPIO 6 to the STM32 SWCLK on DCLK PA14, and GPIO 7 to SWDI on DIO PA13. Critically, we also tie GPIO 1 to the NRST pin, which completely addresses the reset line being tied to the onboard button. Oh, and never, ever forget the shared ground. Without a shared ground between the two boards, your data signals will just be useless floating noise.
All right, Section 3, OpenOCD and GDB setup, navigating STM32 Cube IDE.
Because the IDE naturally expects a proprietary ST-Link, we actually have to manually tell it how to talk to our custom Shrike Lite CMSIS-DAP probe. We first configure OpenOCD as an external tool. Go into the IDE's external tools configurations and set up OpenOCD to launch with our specific target configuration file. The absolute key here, make sure it listens on port 3333 and leave the working directory completely blank. This sets up a local server running in the background, acting as our bridge.
Next up, we tie the GNU Debugger, or GDB, to that exact bridge. In your debug configurations, create a new GDB hardware debugging profile. Select Use Remote Target and set the debug server to generic TCP/IP, pointing to localhost at port 3333. Now, GDB knows exactly where to send its commands to reach your STM32 chip.
Which brings us to Section 4, slaying the configuration bug, troubleshooting crashes.
It is time for the boss fight against those notoriously cryptic software crashes that always seem to plague custom setups. You might be staring at your screen in pure frustration, asking, why is the connection immediately dropping the moment GDB tries to take over? You click Debug, OpenOCD says Connection Terminated, and GDB throws a generic error. Well, what's happening is that the IDE is trying to send ST-Link specific reset commands to a generic OpenOCD server, causing a fatal clash.
Here is the exact fix. To solve raw GDB no symbol table loaded and OpenOCD disconnect loops, you must explicitly uncheck Reset and Delay in your Startup tab. Then clear all initialization commands entirely. Literally make sure the box is totally blank.
Finally, check load symbols and point it directly to your project's binary ELF file. By doing this, we're letting OpenOCD handle the reset and flash loading automatically when it boots, which completely stops the IDE from sending crashing commands over TCP.
And now for the best part, Section 5, Live Debugging Victory, Hardware Success.
All those steps, the firmware flashing, the careful wiring, the sneaky IDE tweaks, they all culminate right here. Because OpenOCD is now handling the reset and flash loading automatically, you can continuously monitor live expressions and step through your C code in real time. Seriously, if you set up a simple counter loop in your code, you can open the Live Expressions tab, hit Run, and literally watch the processor registers in your variables update live without ever pausing the execution of the chip. It's like having X-ray vision for your hardware.
When you contrast the steep price of dedicated proprietary tools with the sheer power of this $4 bare metal debugger, the value is just absolutely staggering. You've just unlocked professional-grade, hardware-level visibility into your embedded systems for the price of a cup of coffee.
So now that you know exactly how to transform a super affordable dev board into a professional ARM CMSIS-DAP debugger, armed with a pro-grade setup and extra money in your pocket, what amazing hardware project are you going to build next? The barrier to entry for deep embedded development has just been shattered. Get out there and start building.